positive charges attracted negative charges, not surprisingly. The reason why it's important that electrolytes are charged ion, no, the reason why this is important is that electrolytes are charged ions found within the body, specifically in fluids. We see it make a difference. Important electrolytes include sodium, potassium, calcium, magnesium, chloride, hydrogen phosphate, and bicarbonate. Bicarbonate, you're going to hear about this one a lot. Bicarbonate is the most important extracellular buffer. In other words, it is going to make something less acidic. So in our plasma, for instance, we have bicarbonate to help maintain a pH, a pH of 7.4, almost perfectly neutral, around 7.4. Our body can make bicarbonate. Our kidneys can make bicarbonate by a process called de novo synthesis. So this is one of the functions of the kidneys. This is something you definitely want to know about. I will tell you this again when we talk about the kidneys, urinary system, but keep in mind that the kidneys do more than just filter, which is huge, but they do more, and this is one of the things they can make bicarbonate, HCO3 minus. By the way, you'll notice that there's a C in here and there's an O in here. Actually, 3 O's, right? That's what that little number means. The subscriptor means there's 4 oxygen, 3 oxygen. If I put a big number in front of this, 2, that would mean that there were 2 molecules of hydrogen phosphate, or if I put a 5 in front of here, that would mean 5 molecules of bicarbonate. That's what that subscript indicates, that there are 3 oxygen molecules. Good thing to remember, because 2 of those oxygen molecules are really the result of metabolism, the carbon. When we breathe in, we take the oxygen to the cells, and of course the cells then use that oxygen to help make electricity, well, ATP, our energy. In the process of metabolism, we create waste. One of the waste products is carbon dioxide. So carbon dioxide then has to move into the blood so it can get back to our lungs so we can breathe it out. I think some of the books will talk about how the hemoglobin molecule will allow for a certain amount of carbon dioxide, and it will, and the red blood cells can help with that. But the reality is most of the bicarbonate actually travels, or most of the carbon dioxide actually travels in the blood in the form of bicarbonate. And then with the carbonic anhydrase at the level of the lungs, it can be changed into carbon dioxide, which then goes out, diffuses out, and we breathe it out. So bicarbonate is something you need to become very, very familiar with. This is one of those things that when you see HCO3 minus, when you see HCO3 minus, when you see HCO3 minus, you shouldn't read HCO3 minus, you should see it as bicarbonate. Do you understand what I mean? When you look at the HCO3 minus in your brain, you should be reading bicarbonate. Acids and bases. Acids and bases are really based around that proton, that hydrogen ion, and how it acts in water, how it reacts in water. Acids have a low pH. The numbers are low. 0 to 14 is the scale, which puts 7 right in the middle. So acids have a lower pH. Bases have a higher pH, closer to the other end of the scale. Acids means that there are a lot more protons, more positive charges. You've heard of stomach acid, right? We have stomach acid that helps to destroy pathogens, which is nice, convenient. We have stomach acid that helps to break down food products. That works out well. If we have too much stomach acid, Well, we want to stop that. We want to make less stomach acid. And so you hear about medications, of course, called antacids, right? You don't want the acids. You'll also hear about medications that are referred to as proton pump inhibitors. Proton pump inhibitors. We are going to stop the pumping of protons. In other words, we're going to have the body make less acid. Pumping of protons. Acids can dissolve metals and literally burn a hole through material. Don't try this at home! Exclamation point followed directly by a period. I think that is unnecessary, but that's fine. Definition of an acid is something that can release hydrogen ions. In other words, there's going to be a great deal of hydrogen ions, free hydrogen ions floating around. Acids taste sour. Bases taste bitter. Bases are also slippery. Think of liquid laundry detergent. Pour some liquid laundry detergent in your hand and feel as it goes through your fingers. Very, very slippery. They can accept hydrogen ions. So you see, bicarbonate can accept a hydrogen ion. Why? Well, because it lost a hydrogen. It doesn't lose, but it doesn't have that proton to balance it out. It has one too many negative charges. So if we throw a positive charge at it, well, then it'll be neutral. But then so will whatever that positive charge came from. Hydroxides are common bases. You'll see those a lot. Hydroxides are common bases. Notice how it reads. For example, bicarbonate can accept hydrogen ions forming carbonic acid, which is a weak acid. The pH scale is relative. So something can be considered acidic, but if you put that next to something else that's more acidic, well then the less acidic thing becomes more basic. So it is very relative. I thought that was a good... I guess this is it. There's a couple of pages in the book dedicated to the pH scale. Concentration or amount of hydrogen hydroxides are measured using the pH scale. The pH scale is from 0 to 14. 0 to 6.9 means there are more hydrogen ions compared to hydroxide ions or hydroxyl ions. Neutral pH, around 7. pH greater than 7 is more alkaline. pH of blood is around 7.4. Grapefruit juice has a pH around 3, bleach around 11. A lot of people are also confused. They think, well, if something is acidic, if it's an acid, well, then it's going to destroy the body. You know, when you want to get rid of the body in the movies, they pour acid on it. The reality is there's not a whole lot of acids that do that. They have to be a really, really strong acid. But a really, really strong base will have a similar effect. It's at the other end of the spectrum. So you can do a lot of damage, and you can see that with a good example of bleach. But bleach can do damage to your skin. You ever dip your hands in bleach for a prolonged period, or work with bleach for a prolonged period, or inhale bleach for a prolonged period? It can do damage. That's a pH of 11, approximately. And the scale goes up to 14. There's a huge difference in those numbers. Even though 11 and 12 are only different by one number, it's a lot bigger than that because the pH scale is on a logarithmic scale. And if you've had math, algebra, calculus, statistics, anything like that, you've probably heard of the logarithmic scale, the log. Okay, so it is there's a big difference between those numbers. And it shows it here. It shows protons in moles versus hydroxyl ions in moles and what the pH of that would be. Moles a standard unit of measurement. Based around, I think it's based around the number of particles that are found in 0.012 kilograms of carbon, which comes out as a number of 6.022 times 10 to the 23rd, big number. But the reason why it was, we have that measurement, it actually makes it easier. It makes it easier to do the math. And the pH is actually equal to an inverse of a log. It shows, I think it shows in the book that it's the pH is equal to the log of 1 over the concentration of hydrogen ions. That's what the bracket around H means. The brackets means concentration. And so that means the concentration of hydrogens is happening there.
Yep.
Okay. The reality is the pH scale is based on the inverse of the log, because it makes it just easier. This pH is equal to, it'll have a minus sign, log concentration of hydrogen ions. Is that in there too? I think that's real. Okay, good.
It's just a function of the exponent.
Good things to know. I'm sorry?
It's a function of the exponent. When you take the log of the negative.
Yes. Which in this case, the log of, what is it, 1 is 0? Yeah. So that's how we end up with a negative. It's read as inverse log, not negative log. Just an FYI. So if you're talking to someone and you say inverse log, they'll say, oh, look how much he knows. Look what she knows. That's good. Regulation of the acid-base balance is things like our lungs and things like our kidneys. Our kidneys do more than just filter. Kidneys are hugely important. The most important organ in the body, of course, is the brain, which is then followed by the heart, which is then followed by the kidneys, in fact. Brain, heart, kidneys. That order. Very important, because if a person is ill with anything, if they have some sort of trauma, the very first thing I think of is, how is that going to affect a person's brain? And then I think, how is that trauma or that disease going to affect the person's heart? And then I think, how is that disease going to affect the person's kidneys? And then with treatment, you treat a patient, the first thing you think of is, how's that treatment going to affect the brain? How's that treatment going to affect the heart? How's that treatment going to affect the kidneys? Incredibly important. Once the kidneys go, the patient has about 2 weeks of life left. Don't get me started on kidneys. There's a lot of dialysis centers in this country popping up. I know, getting started on kidneys. But this is one of these things that's just incredibly frustrating, because we see all these patients who have chronic renal failure. Almost 90% of all the patients in the United States who have chronic renal failure have chronic renal failure because of diabetes. It's kind of a big deal. Which means if you go into a dialysis center and you start picking up charts, probably 9 out of 10 of them, diabetes, 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 diabetes. And of course, about 70% of those are probably going to be type 2, which is something that could have been prevented. And we're probably getting wheeled in a wheelchair because they had to cut off one of their legs. And they probably have cardiomegaly because of atherosclerosis, and they're probably blind or going blind because of the blood vessels and the nerves that are destroyed retina. So it's incredibly frustrating, because if you can have patients who just listen to what you say, eat less, exercise more, eat healthy foods, don't eat all that garbage with an occasional Saturday donut is fine, but otherwise, all that other garbage, just follow these basic guidelines that every one of us has learned in kindergarten. And it's amazing how we can stop that from happening. But that's frustrating, because when a person is on dialysis, what are they waiting for?
Kidney
one of two things: kidney transplant or death. That's it. Patient on dialysis. That's all they're waiting for. Horrible. It used to be when people would go on, when dialysis was first started years ago, a person would go to the hospital to go on dialysis and they wouldn't leave. They were constantly on dialysis forever. So we live in an age where people can go in, have this done after a couple of hours, and then they're wiped out for the day. And then of course the rest of their, they do this 2 or 3 times a week, and then the rest of their week is other doctor appointments, other things. Horrible. And if you ask them, what would they have changed differently in their lives, they would probably say, I would listen to Dr. Sturgeon. Or the other doctors, or my kindergarten teacher who told me, eat healthy fruits and vegetables, follow this pyramid, exercise more. That's it. Very simple. No, it's simpler? Driving through the drive-thru, right? That's simple. You don't have to get out of your car. That's easy. Sitting on a sofa, watching TV, or playing the Video X PlayStation box games. Clearly, I don't know what they are.
That's not the cable play.
All the except for the Wii, and now there's the one that you jump around a lot too. I don't know. Great ideas, great concepts. Unfortunately, I don't know if people are utilizing them as much as they could. But it's a very simple equation, and just people don't follow that. And so here they are. They thought they were doing things easy, a long time ago, and now they're in a position where their life is just miserable and more difficult. We want to take care of our kidneys, and this is a big way to take care of our kidneys. Ladies, of course, you've heard of drinking cranberry juice, right? That's more for urinary tract infections, but it stays true. Drink the cranberry juice, not the cranberry juice cocktail, cranberry juice. Not the cranberry vodka, not the cranberry with the apple juice and the other juices mixed together. Straight cranberry juice changes the consistency of the urine. All right. The rule of the respiratory system is take in air and get rid of carbon dioxide. I think we know this. Hopefully we understand this. We breathe in air, but we really don't want air. What do we really want? Oxygen. We want oxygen, right? We breathe in air, but we really want the oxygen. That's kind of the most important. There's other gases in here. Helium, hydrogen, nitrogen, carbon dioxide, carbon monoxide, probably lots of other ones. How much of this room air is actually oxygen? About 21%. So when you take that deep breath of this room air, you're getting about 21% of oxygen. Now, are you using all that oxygen? No. Of course, some of it's going to go back out. But we'll see that. Carbon dioxide, as we stop breathing, there's a buildup of CO2 in the body, and there's buildup of acids detected in the brain, which gives you an overwhelming desire to breathe. Where are you going? That was planned. I apologize for that. If there's a problem with the respiratory system, kidneys can help out with the extra de novo synthesis of bicarbonate, and that will give us a higher pH, which is good if we have an acidic pH. All right. Getting those elements and putting them together, forming molecules, creates bonds between the atoms. If an atom donates, if it gives up one of its electrons, then we end up with something called an ionic bond, which makes sense because sodium alone with the positive side is an ion. Chloride alone with the negative side is an ion. Put the two ions together. One will donate, and we end up with an ionic bond. And if you look at the sodium chloride at the bottom there, the bond between sodium chloride and table salt is an ionic bond, and if sodium chloride would dissociate, it would form sodium positive ions and chloride negative ions, respectively. Understand that when we talk about molecules, we talk about these atoms that are joined together, that doesn't mean that they're always in that cube of salt. That doesn't mean that every molecule in there is joined together. At any given time, we're going to find a certain number free sodiums and free chlorides. They'll disassociate and associate depending upon the environment they're in. Excuse me. Under some environments they're going to dissociate a lot more rapidly or a lot more, and others they're not going to dissociate very well at all. But there's always going to be, a certain number of these molecules that are not going to be joined together, or will separate and then come back together and separate. So at any given time, you can see. That's why when you see these chemical formulas written, you often see an arrow going in both directions. Here we have sodium helping out chloride. Now what we have is a nice balance of valence electrons. The outer ring, in this case, of electrons, we see that we had an uneven number in both, and now we have an even number. Very OCD, actually. Doesn't like to be uneven like that. If the electrons are shared between atoms, if they cohabitate in the valence ring, if they're going to cohabitate in the valence ring, then we say they are covalent bonds. Does that make sense? They're going to cohabitate in the valence ring. They're covalent bonds. Sometimes covalent bonds may be unequal. That causes what we say is a polar covalent bond. The polar molecules are going to have charges on different parts of the molecule is going to be charged differently. We see this like in water, right? By the way, water is made up of how many hydrogens? Two. There's an H, and then there's a small 2, right? And then there's a big O. So we have hydrogens and oxygens. Specifically, we have 2 hydrogens for every oxygen. You've seen the oxygen or the water molecule, right? If you have background in chemistry, it's very, very obvious. One big oxygen with 2 hydrogens stuck off the side, so it looks like a Mickey Mouse. The big things. Okay. In that water, in the water in the lakes, in the water in the ponds, in the water in the streams, in the water in your fish tank, you have fish swimming around. Fish, of course, need oxygen, but they do not get their oxygen from outside. They have water passing through their gills, and they extract the oxygen that way. But not this oxygen, not the covalently bound oxygen. That would be difficult. Not to mention, we would end up with an interesting, we'd end up with an interesting, very dangerous situation. But, sorry, in my head it was funny. What happens is the water going through the gills actually is extracting free oxygen molecules. That will somewhat bind at these polar ends of the water molecule. That's why if you want to keep fish alive in the tank, you have an aerator, right? And the little thing that blows bubbles. So what it's doing is literally is putting oxygen, free oxygen molecules into the water so the fish can extract them. They do not break apart the covalent bonds, the polar covalent bonds of a water molecule. That would be difficult. A single bond looks just like that. Formation of a single covalent bond. They're sharing those electrons. Double covalent bonds, a double bond looks just like that. Notice how it's drawn off to the side. Hydrogen to a hydrogen is 1 bar. Oxygen to an oxygen is 2 bars. That equals. That means a double bond. Here we have that carbon that I said loves to have 4 things attached to it. Notice how it has a carbon, 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 carbon. Like this. If it had, let's put an R group over here. If it had something like this, then this carbon has 2 things attached to it. The R just represents a group of another part of the molecule over there. So this carbon is going to have 1, 2 things attached. It wants to have 4. This is what it likes. That makes it happy. So we put hydrogens here. I talked about this the other day. And of course, since this carbon only has 1, we're going to put 3 hydrogens on it. Now, in chemistry, you learn that when you write these out, you don't have to include writing hydrogen up there because it's implied that it's there. But when you're first learning it, you see it written like this. And I brought this up when we were talking about the fats. And I said that these carbons have a complete number of things attached to them. They are completely saturated with things attached to them. So this is what the chain of a saturated fat would look like.
That circle thing?
That's
Just checking the demo.
this way. All right, so let's take off a couple of these. If we take off a couple of those hydrogens, well, then we have carbons that are not very happy. This only has 1, 2 things attached to it. This one only has 1, 2 things attached to it. So what it will do is it will create another bond right here. It will create that double bond. So now this has 1, 2, 3 things attached. This has 1, 2, 3 things attached. So we'll put 1 hydrogen here, 1 hydrogen here. Oh, shoot, both on the same side. 1 hydrogen here. That double bond causes the molecule to kink. That kink in the molecule is what keeps that fat fluid. This is what we'd say is an unsaturated chain, because it does not have all the carbons that it could have. This is the cis configuration. And both of the hydrogens are on the same side of the molecule. And this is the trans configuration. So people talk about trans fats, at least you can have an idea of what the molecule is going to look like. And that it really doesn't make that big a deal if all you did was kept your overall fat intake low, it wouldn't make a difference. Okay. So we see carbon totally saturated there with hydrogens, as it likes to be. Ionic bonds, electrons donated. Polar covalent, unequal sharing, covalent sharing. Water, H2O, cheap liquid. Water is incredibly important. How important is water to life? I'll tell you how important water is to life. When NASA puts together billions of dollars and flies a little go-kart to another planet, what do they look for?
Water.
They look for water, or signs of water, or evidence that water existed, because that would indicate the possibility of life, at least as we know it, right? So that's why they're looking for some trace of water, because if water is there, then life could be or could have been there in some form. Water is a polar solvent. It has those somewhat unequal charges. Dang it, I think they have a picture, right? Yeah. Yeah. What page is that? 46 in the textbook. They show the water molecule. You can see how there's, on that molecule, there's different charges, different sizes of the molecule. Charged molecules contain things like oxygen, phosphorus, nitrogen mixed with water. Such molecules are what we call hydrophilic. If it mixes with water well, it is hydrophilic. Can't tell you how important this stuff is to know. If it doesn't mix with water well, if it is afraid of water, scared of water, we say it is hydrophobic, like fats and lipids. Stay away. Oils. There it is. Okay. Good. You can see how the charge, this water molecule here, this is, what you see in a drop of water. You see how this part of the molecule over here, part of the whole molecule is more positive on this end, positive over here, but negative over there. bond between water molecules increases water's heat capacity. It can store heat. Heats up slow. Cools down slow. When one substance is dissolved in another, combination is called a solution. The thing that we dissolve in is called a solute. A solute is a solid particle dissolved in a solution. That's the best definition. A solute is a solid particle dissolved in a solution. A solute is a solid particle dissolved in a solution. Now, we're familiar with this concept. We've gone to the beach, jumped in the ocean, got very, very wet, came out of the ocean, didn't get a towel, just walked around in the sun. It was 90-some degrees outside. The water evaporates off your body, and you still feel all this little grittiness all over. What is that grittiness?
Salt.
Mostly. It's salt. Where did the salt come from? It was dissolved in the water. You ever leave the Kool-Aid? You get a glass of Kool-Aid when you're a child, or now, and you leave a little bit in the glass, just a tiny bit at the bottom of the glass, and you leave the glass out overnight and the water evaporates out. What's left?
Sugar.
Bunch of little solid particles, right? It's sugar in the coloring, basically. And what do? Well, they precipitate it back together. They're more attracted, to one another now that water is left. So you end up with this little crustiness at the bottom. Man, that's important. Because when you put, you ever see those little crystal light packets you put in a bottle of water, they're about this big, tiny little thing. You pull the top out, put it in a bottle of water, shake it up. Get one of those tiny little things of cherry pomegranate flavor. Pour it in the bottle of water, shake it up. What color does it turn the water? The cherry pomegranate.
Red.
No, it does not turn the water red. Water's not going to change its property just because you poured some of that in it. What color is the water? Water's still clear. What colors make the water appear? It makes the water appear red. But you did not change the water. You're not that good. Do you know how we know this? Because if we evaporated that water out, would it evaporate in color? No, it would evaporate like water does. And what would it leave behind? All of the things that cause that color to happen. And if we were to look at that water that appears red under a very, very strong microscope, we would see clear water and a whole bunch of little tiny red dots. The things that are making that color red. Under a very, very strong microscope, under a light microscope.
Well, then it would be false.
I'm sorry?
Then it would be false color and it would actually be red.
Well, yes. Stop being scientific. You're confusing me now.